Did you know that the antioxidants we eat in food can also be used in the manufacture of plastic? These additives, which occur in nature and can delay aging in humans, can also have a similar effect on plastic. Are you surprised? Well, I certainly was. Our next speaker will introduce us to this topic. Please join us in welcoming Professor Dr. Rudolf Pfaendner, Head of Plastics at the Fraunhofer Institute for Operational Skill and System Reliability.
In meinem Vortrag heute möchte ich Ihnen
In my presentation today, I would like to talk about efficient additives for plastics from nature. And in this context, I think it is very important that to know that it's not only biopolymers, as it's entitled in the conference, but bioadditives are a very important area in the field of plastics and will become even more important. First of all, some general remarks about our institute. In our institute, we cover the whole value chain, starting with polymer synthesis, additive synthesis, then we work on formulation, material characterization, component investigations from different systems. Of course, this includes numerical simulation and digitization. But we're not limited only on plastics, but metal and compounds. In my presentation, I would like to talk about history. Are additives known from renewable sources? Is this an old story? Then I would like to talk about new systems, especially suitable for polyolefins, and I would like to talk about new stabilizer systems for recycled plastics. Then I would end with some conclusions. So let's look back first of all. Looking back, we find that the first thermoplast known as celluloid could only be realized by using bioadditives. Celluloid consists of cellulose and wire, and this is a material which can't be processed thermally. And the brothers Hyatt found if I add camphor to the cellulose nitrate, a material from nature, then I found characteristics which could be processed thermally. And from today's point of view, you may add they added additives, plasticizers. Out of this easy invention, plastic additives derived. And we know today, and this holds true for all kinds of plastics, that additives are not only important, but they guarantee plastic properties so that they will be maintained during processing and during use, and that new plastic properties for new applications field may be extended. Today, in a world of biotransformation, which is also true for plastics, of course, it becomes clear that the need for bioplastics will increase from renewable resources. At the same time, it means that the demand for additives will increase. Talking about additives from renewable resources, of course, they are suitable for fossil-based plastics, but also for natural-based plastics. And the other good news I would like to share with you is that with the increase of implementing biotechnological processes, raw material for new additives will become available. Materials for plastic additives from nature are not new. You may be familiar with a lot of different examples, starting with plant fibers, wood, cellulose fibers, used as fillers or reinforcement agents in plastics even today. Plasticizers and nucleating agents based on starch or sugar are part of today's technology. Oils and fats, glycerol are used for lubricants, anesthetic agents, plasticizers, PVC stabilizers, antioxidants, and there are numerous more exotic chitin chitosan used as biocides and applied today. Let's start with an example. Plasticizers. The market share of bio-based plasticizers amounts to approximately 1 million tons, so more than 10% of the market. This is more than the share of bioplastics in the whole plastic industry. Examples for bio-based plasticizers is epoxidized soybean oil known for decades, sebacic acid esters, succinic acid esters, citric acid esters, or isosorbate esters, all available in the market. One of the most important fields when it comes to additives are antioxidants. They consist of phenol structures, sterically hindered phenol structures, and these phenol structures can be found everywhere in nature. Typical examples are vitamin E, cardinol, which is available from cashew nuts, caffeic acid, of course, could be found in coffee, ferulic acid, but flavonols and respective glycosides, polyphenols, which can be found in different food, tea, extract, rosemary, red wine, or even tomatoes. Why do we need antioxidants for plastics? Plastics is nothing than organic substances and compounds, and as we all know, human beings are aging, so do objects like cars, and of course plastics are aging, as you can see here in this example. Antioxidants for plastics can prevent aging or delay aging. During processing and use, the age of plastics, which is caused by autooxidation and which led to a loss of properties and value, is prevented. This all starts with processing without degradation and without loss of properties if special additives are added. Furthermore, antioxidants are essential to maintain properties during the long-term use. And of course, we wonder whether antioxidants, called bioantioxidants, are they useful for the stabilization of polymers? Can they be used? And here, using the historic example, vitamin E, typical antioxidant, very beneficial for humans and cells, delaying aging of human cells. And of course, this is also good for plastics. And there are some old data I would like to show you, giving you two examples. First, LDPE and PP in comparison to antioxidants. You see the structure on the right-hand side. First of all, let's look at LDPE. LDPE with aging increases the molecular weight. That means MFI is decreasing. In this picture, or in this slide, you see if I have LDPE, if I do not add an antioxidants in processing LDPE, the melt flow will decrease by 17 to 18% after 4 extrusions. With an addition of normal antioxidants we call mono or tetra, then the degradation will be reduced to 5 to 10% only. and then adding vitamin E in the same concentration, then the degradation is even lower, as you can see on the left-hand side. That's to say, vitamin E, in this example, LDPE, is a very good stabilizer, which is even better, performs better, and with a better effect than the normal antioxidants.
Die andere Seite ist natürlich die
The other side is the long-term heat stabilization. And you see this on the example of PP on the right-hand side. Normally, you test under higher temperatures, here 135 degrees and 150 degrees in red. You see that without antioxidants, we see embrittlement within hours, not talking about days.
Wenn wir jetzt unsere herkömmlichen Antioxidantien,
So if we add the normal antioxidants mono and tetra with 135 degrees with this tetra substitutes products, we have 160 days until embrittlement. So an increase compared to the material without additives. Also, vitamin E leads to an improvement. However, only to 10 days. So we conclude that the natural antioxidant vitamin E is a very good stabilizer when it comes to processing, but it is not good for stabilizing long-term products. So what can bioantioxidants compete with standard processing and long-term thermal stabilizers? Today's standard solutions are very often combinations of phenolic antioxidants and phosphites. Normally, it is an addition of a general primary and secondary stabilizer. Of course, other additives are in these plastics. Now, if this is state of the art and the selection of the market, then we ask ourselves, are synergistic combinations with appropriate alternatives to phosphites, could they be found in nature? As we saw, phenols with alternative structures from natural resources are available. The problems are phosphates. Normally, they are not to be found in nature. There are good reasons for it. Phosphates in a plant or wherever would be transformed to phosphate under air, and then as phosphate it can't be used as a stabilizer any longer. It's non-effective. That is why we have to look for synergies, synergistic combinations with special effects. Fortunately, we found something in our institute. That's to say, novel synergistic stabilization systems could be developed based on renewable resources to 100%. On the one hand, they consist of natural polyphenols as shown, and on the other hand, they consist of polyols, alditols or cyclitols. And you see just a general structure on the right-hand side. Compound sugar molecules which contain a lot of OH groups, a combination of primaries and secondaries. So what can these compounds do? Let's first look at this one stabilizer system. We apply a twin screw extrusion at 200 degrees and a polymer, here polypropylene, 30 minutes in circles. That's to say, the load to our plastics is 30 minutes at 200 degrees. We measure the degradation of the material by reducing the residual torque. The lower the residual torque, the higher the damage. The higher the residual torque, the better the stabilization. So what could be found? First of all, if there's a polypropylene without stabilization, of course within 30 minutes, 200 degrees, there is a high damage. That's to say, the loss of the residual torque is at 70%. Adding the usual stabilization with phenolic antioxidants or phosphite, here P1, then we will see an improvement. We have 60% of the original value still after this 30 minutes. If we add polyphenol alone, we see an improvement against the non-stabilized material. However, if we have a low concentration here, 0.1 only, it is not as good as the classic combination of AO plus P1. If we add alditol only, then, well, we have a slight improvement only. The huge leap forward is by combining polyphenol and alditol at the same concentration. And we reach values of 60% or even more. That's to say, at the same concentration level, this material combination of renewable resources material is as good as classic combination AO plus P1. If I double the concentration, even as you can see here on the far right side, then after 30 minutes testing time, I have hardly any loss at all. So you may wonder, well, with vitamin E you may have the same effect because of processing stabilization, it was the same. What's best? So to answer this question, we have to look at the long-term thermal stability. And you see that very good here in this slide. We do the same test. We do a testing body using them at 135 degrees over a certain period of time, as long as this test is if there are no mechanical properties any longer. In the usual combination out of AO plus P1, we reach 1.1%, 400 hours until embrittlement. If we double the concentration, then we have 1,000 hours. If we add the same concentration of polyphenol, then the result is worse than compared to the classical combination. But if we use the new system consisting of polyphenol and alditol, then we see in the long-term thermal stability the classic properties. We can keep the classic properties or even outperform them. First of all, we have to understand that recycled plastics are different to new plastics because very often they have a pre-damage by oxidation, photooxidation, degradation of molecular weight or other structures, differences in structure. Furthermore, recyclates can be found of different formulations, different technologies, processes, and thus they are non-identical to a pure new material. Very often, with high-value methods, recyclates show impurities, for instance, by foreign polymers or other materials, could be paper fibers, glue, residues, and so on and so forth. That is why recyclates require an adjusted stabilizer system. A stabilizer system, which is not identically, especially cost performance with the stabilizer system, normally used for new material. And here we could prove that the stabilizer systems based on natural phenols plus alditols and cyclitols are able to address pre-damage, and as I said, here for the first time we have the possibility to use renewable materials, 100% renewable materials. In this case, here it's a multiple extrusion, and here we measure the melt flow, 3 extrusion passes. The more stable and the lower the melt flow, the better the processing stabilization. Here, looking at the orange curve, you see that the non-stabilized recyclate after 5 years of usage, which was in contact with acid, that this battery material without additives, after these 3 extrusion passes, goes from 9.5 to 11.5, whilst with the commercial recyclate stabilizers, it shows an effect, it's stabilized, but here the melt flow after first extrusion is much higher, and with the new combinations, as you can see here in green, right from the beginning we have the lowest melt flow and the best stability right from the beginning, and even after 3 extrusion passes you see there is no change. Here for recyclates it's an outstanding stabilizer system available. I showed that bioadditives are a very good alternatives to commercial combinations. Nevertheless, we have to say that additives from natural resources do have downsides, or that you have to enter compromises. Let me give you some examples for this. First of all, the development of color, discoloration, because by impurities or by double bonds found in nature, this may harm the color. Plastics, it is necessary, especially talking about bioadditives, it is necessary to use mixtures. Nature does not make any difference between it is C16 or C18. It uses whatever is available. And this composition and impurities depend on the natural growing conditions. Very often, thermal stability of bioadditives is limited. It is lower compared to commercial additives. At the moment, we are currently working on a project to improve thermal stabilities. But the systems I introduced to you for polyolefins can be used to temperatures of 280 degrees. One other challenge is the access to identical quality, identical stable compositions and supply. And of course, they have to be built up. So this brings me to conclusions. I think additives from renewable resources, bioadditives, are well established in several standard additive classes. This includes, for instance, lubricants, plasticizers. I think looking at all biotrends, we will see good growth options in the future. I could show that bio-antioxidants provide very good stabilizing performance. I could show that our new synergistic systems, fully based on renewable resources, can compete with today's standard systems. And I could also show that excellent processing and long-term performance in polypropylene and polyethylene and recyclates formulations is proven. Thus, having said, I would like to say thank you to all my team and colleagues mentioned here on the left-hand side, and I would like to say thank you to you for listening.
Thank you very much, Professor Dr. Pfaendner from the Fraunhofer Institute, for your interesting insights and findings. And a very warm welcome. Hello. Thank you.
Hello, thank you.
Thank you for joining us online and for being with us. We would like to start a discussion, and my colleague Martin is happy to pass on the questions from the audience to you.
Yeah, thank you very much for this very interesting topic. Here comes a question from Raju, India. Are the bio-based additives you have food contact approved? So do you see any chance to pass a food contact approval?
I think so. Some of these molecules which we have identified are in fact food additives today. So it should be quite easy to get food contact approval, of course, according to the regulations in each country. It has to be added for plastic applications, but there's a good chance to get that.
Oh, that's quite good news. The next question from Amol, India. What are your views on natural fiber-based polymers on lightweight, especially consistency of those fibers and the processing window? Can your additives contribute to that as well?
The additives which I've shown today are mainly focused, let's say, on processing and long-term properties. However, we had in our institute as well projects on natural fibers as, of course, reinforcement agents for polymers like polypropylene or polyethylene. And there we work mainly on adhesion promoters to get a better adhesion between the polymer matrix and the fibers. So there are data available on that side, but it's different from what I'm showing today.
Okay, got your point. My question would be, for sure, for the audience of biopolymers, it would be also very interesting to see the impact and also the possible usage for compostable materials. Is there any schedule already done or some preliminary results you can disclose to the audience?
Of course, biopolymers and biodegradable polymers are part of the project. And what we are doing there is we try to control the lifetime. So on the one side, we can provide additives which can increase the lifetime, for example, of PLA, so that it can be used as an engineering thermoplastic. On the other side, we have developed, which I've also not shown today, accelerating additives which can shorten the lifetime of, for example, PLA, that it is much faster compostable and as well compostable at lower temperatures. So at the end, what we try to cover is a full control on the lifetime of a polymer like PLA or like other bio-based polycondensation products, to be more general. And according exactly what is wanted through our customers. If somebody wants a short lifetime, we can provide an additive. If someone wants a very extended lifetime, we can as well supply an additive package for that.
Very interesting. I think that's what the market is really looking for. Is there also any plan for commercialization of your products together with partners?
Yes, fortunately, we have an industrial partner where we will upscale and then commercialize some of the selected products which we have today in the pipeline. We, as an R&D institute, of course, we are focusing on applied research. However, Fraunhofer will not sell additives or any product in this case. So we need an industrial partner, and for the developments as well for bio-based additives as well for recycling additives, we have an industrial partner where we have a very close cooperation, and we expect commercialization, let's say, within the next year or so.
Yeah, very interesting. I hope we have the chance to get you for the next polymer processing and molding conference to get us more insights and hopefully the commercialization and results on that one. At least I'm curious to hear that from my point of view. I'd like to thank you for the discussion and looking forward to stay with you in contact via the Polycom EV. If there are further questions, we would be very happy to transmit them to you after that conference.
Of course. Thank you very much for the invitation and for giving me the opportunity to talk here. And if there's any question, I'm happy to answer it.
Okay, thank you very much for joining us and have a lovely day. See
Thank you. Same to you.
Thank you very much. Bye.